Okay, good morning, everyone. How did the assignment go? Any questions about the homework? Please put them on chat. Okay. All right. Okay, we start with those and we proceed. So number 31. So the two main formulas basically we did yesterday were the following. The derivative of ln of x and the derivative of and the derivative of a to the x, which is the ln of a to the x. Okay, so those were the two main formulas we did yesterday, and let's do the homework. All right. So we'll do that. Number 23, we had y equal ln of x plus 1 over x minus 1. Okay. So, okay, what do we see when we see that? Now it's better. So what do we see here? The minute we see this, we see ln of something. It means we immediately have a, we immediately have a chain rule situation, and that's really my inside function. That's my inside. So I have my u, my inside, to be x plus 1 over x minus 1. And my inside is the ln function, ln of u. So the derivative is going to be, just dy dx is the derivative of the ln evaluated at the inside times the derivative of the inside. Okay, so the rest is we have to find the derivative of the inside, and we need to do some algebra here. So this is going to be equal to, now, 1 over x plus 1 times x minus 1. This will become x minus 1 over x plus 1. Okay, but just properties of fraction from here to here. Now, from here to here, it's the derivative. That's a quotient. To find the derivative, you have to use the quotient rule. The derivative of the numerator is 1 times the denominator minus the numerator times the derivative of the denominator divided by the square. So finally, I end up with x minus 1 over x plus 1 times plus x minus x cancel each other, minus 2 over x minus 1 square. So it's just a bit of algebra. This and this simplify, we end up with minus 2 over x plus 1 times x minus 1. Okay. All right, let's do some others. 25, 24. Okay, I'll do either one, either 25 or 24. They are basically the same. So I will do 24, for example, and then I proceed to the others. So y is x, ln of x minus x. Okay, and we have to find the derivative. Okay, we look here. We have derivative of this expression minus the derivative of that. This is a product, x times ln. So to find the derivative of this expression, I have to use the product rule. Derivative of x is 1 times the ln plus plus x times the derivative of ln, which is 1 over x. And this would leave me with ln of x plus 1 minus 1, which is ln of x. Okay? All right, now we look at 31, 33 and see what they are about. Okay, so they are all application of chain rule and quotient rule and stuff like that. So this is ln over ln plus 1. Okay, again, what do you see quickly? What do you see here?
Quotient
What do
rule.
you see? What?
Quotient rule.
Immediately, that's a quotient rule. So what is the y prime? The derivative of the numerator times denominator minus the numerator times the derivative of the denominator, which is 1 over x. The whole thing divided by that square. Okay, and this will give me quickly, we're going to multiply 1 over x times this, we distribute, plus 1 over x minus that over this quantity squared. Those and those do cancel each other out, and this would leave me with 1 over x over the squared, which is basically, if we use the property of fraction, it's 1 over x times ln of x plus 1. All right. So, okay, we finalize with 33 and 34. Okay, 33 is y equal x to the power e. Okay, so what's the derivative of x to the power e? Okay, back to you. Go ahead, I'm listening. What's the derivative of x to the power e? What type of function is that? No, you guys are very quiet.
We use the power rule.
That's the power rule, absolutely. That's the power, that's the number. No more, no less. So it's going to be the power times x to the power minus 1. Okay, so that's much more than the power rule. Okay, now finally, number 34. Y equal e to the x times x to the power e. So here, basically, they are making sure that you don't confuse powers with exponential. That's really the goal. So that's a product rule immediately. And my derivative is e to the x times x to the e plus e to the x, the derivative of x to the e, which is to the minus 1, and of the problem. Okay. Any other questions? All right. So today I will talk a little bit about derivative as a rate of change, and then we're going to move to the last bunch of formulas, and after that we go and start doing application to the derivative. So we're almost at the end of the formulas. So derivative as a rate of change, I started it a little bit yesterday. I will do another example. Okay, and the main idea here is, I mean, this is a little bit harder than before, but we're heading this way, that you have to think derivative of the derivative as a velocity. So that's what really help you understand it. The velocity tells me how fast distance change. The derivative will tell me how fast the output changed with the input. That's really what it is. So yesterday we took the example of bacteria growth, if you remember. So we took this example. It was 10 times 2 to the power t. And P of t represented the population of a bacteria. So and we evaluated, for example, P prime at 1, and we got like 13. point something. And the unit was the unit of the population per unit of time, which was hour. So that's always the unit of the derivative. It's the unit of your output, which is population per unit of the input. So this tells me that around t equal to 1, think of this like velocity. It means when t equal to 1, the population is changing. How fast it is changing? It's changing at the rate of 13 bacteria per hour. When we computed the derivative at 10, it was like 7,073 bacteria per hour. It means at 10, the population was really growing at a way faster rate at 7,000 bacteria per hour. So giving unit to the derivative will help us start interacting with it. So how fast population changes with time at the rate of 7,000 per time. Okay. Now I'm going to do one more exercise. It's a little bit harder, but I would like to do it because we're going to hit a section, and to understand the section, we have to understand the derivative as rate, how fast things are moving. All right, so we're going to consider the following problem. Very simple. We understand it. Suppose I take a circle. The area of a circle changes with the radius. Does this make sense? So you have a circle, and its area, as you change the radius of the circle, the area changes. So this is my circle. Okay, and that's the radius. You change the radius, the area gets bigger. You change the radius, the area gets bigger. So the area already changes with the radius. Okay, and there is a formula, of course, that relates the area with the radius. So the area of a radius of a circle is a function of the radius. So it's pi r squared. And let us assume r is in centimeter. All right. So my first question to you is the following. So we're going to take another piece of paper. Okay. So question number 1 is, so that's the area, is pi r squared. Suppose I tell you find, and that's the graph of the area with respect to that's the radius, and that's the area. Find the average rate of change. So on average, find the average rate of change of the area with respect to the radius for when the radius is between, let us say, 2 centimeters and 5 centimeters. Okay. So as the radius gets larger, my area definitely is getting closer. So as the radius change from 2 to 5, on average, the area by how much is changing per centimeter? So let's do that, and you guys will give me the unit attached to it. So what is the average rate? It is the area at 5 minus the area at 2 over the 5 minus 2. And we plug in those numbers into the calculator, and we get the following. So that's the change of area, how much the area changed from here to here, over the change in radius. So this is going to give me the following. If you guys have a calculator, it will help if you help me with that. So it's going to give me 65.97 divided by 3. It's giving me 21.9. All right. Now, what's the unit? What's the unit of the average rate? Think about what we did mathematically and assign unit to the average rate. No? What's the unit of the numerator? The change in area. What's the unit of the numerator? The numerator is centimeter square. Okay, because that's how much the area changed. What's the unit of the denominator? unit is centimeter. Right. So the unit of the average rate is centimeter square per centimeter. It means what your classmate wrote is exactly correct. It means on average, the area on average, when the radius change from 2 to 5 as the radius get bigger, on average, the area is increasing by almost 22 centimeters square per centimeter increase in radius. It means on average, every time the radius change 1 centimeter, every unit change in radius, the area grows by 22 centimeters square on average. Okay, that's right. So it's not centimeter square, it's centimeter square per centimeter. How fast, on average, the area change with respect to the radius. So that's really the unit of the average rate. Unit of output, it's unit of the output, centimeter square per unit of input, which is centimeter. Okay, and that's really on average. It means, okay, the radius grow, the area grow, it's averaging 22 per every time the radius change by 1 unit, that's what's averaging. Now let me ask you the following questions. Do you think the area grows faster when R is 2 or when R is 4? So what do I mean by that? Suppose the radius is 2 and we increase the radius by a little bit. The area grows. Suppose the radius is 4. The radius is 4. And we increase the radius by a little bit. The area is going to grow. So I might ask the following question. When does the area grow faster? When I increase the radius from 2 to 2 plus a little bit, or from 4 to 4 plus a little bit? When is the area growing faster? So if I go from here, I add a little bit of radius, the area changes a little bit. If the radius is 4 and I add a little bit, the area is going to grow. When does it grow faster? 1, at 4, or at 2? Area grows faster at 4. Exactly, because even the picture tells you. The picture tells you it's growing faster at 4. Now we're going to find the derivative at 2 and the derivative at 4. And this really gives me an idea how fast is the area growing here versus how fast it's growing here. That's really what the derivative tells me. How fast is it growing at 2? On average, 22 between 2 and 5. Sorry, I'm going to do it at 5 here, not 2. Between 2 and 5, it averages at 2. But when the radius is 2 and we increase a little bit, the area is not going to grow by 22 centimeters square per centimeter, definitely less. So think about velocity. That's really the idea of velocity. It means here, the velocity at 5 is much faster than the velocity at 2. So the real idea that derivative is a speed, but here is the speed of the area with respect to the radius. So we're going to compute the derivative at 2. And we're going to compute the derivative at 5 and see really what's really happening here. So what's the derivative at 2? Now I cannot compute the derivative at 2. I need to find the formula for the derivative. Now the derivative is pi times r squared. R is in this case, R is my variable. And the derivative is pi times 2r. It means that's the derivative. So at 2, the derivative is 2 times pi times 2. It means it is 4 pi, which is almost 4 pi. It means 4 times 3, basically. It should be like 13 times something, of 12.56. And a prime at 5 is going to be 2 times pi times 5, which is 10 pi. 10 pi is going to give me 31.4. Okay, now what's the unit? What's the unit? the unit of the derivative is the same as the unit of the average rate. It means the unit of the derivative is, because the derivative is nothing more than limit of average rate. The unit is unit of the output, which is centimeter square per unit of input, which is centimeter. So here the unit is centimeter square per centimeter. It's important to know the unit because it gives meaning to the derivative. Okay, so the derivative here is 12.56 centimeter square, that's the unit of the output, per unit of input. Crucial to understand it. It means when the radius is 2, of course, the area is growing here. How fast it's growing at 2? It's growing at the rate of 12.5 centimeters square per centimeter. So, however, when the radius is 5, the radius is growing at the rate of 31 centimeters square per centimeter. So we know that on average, it was 29.99. That's really the average between here and here. But how fast it was growing near 2, it wasn't growing very fast. It was growing 12 centimeters square per centimeter. However, later on, it's 31. So it averages that much, but the growth, the fastest growth was happening right here. However, here, the growth was not very low. So what the derivative really give me is how fast the area changes with respect to radius. So the notation for the derivative will be here, dA, how fast area, dr, how fast this changes respect, and this is here at r equal to 2. So how fast area changes with radius. Okay. So I finalized this idea, which is we're gonna, of course, eventually come back to it, but I cannot start the next section before talking about that. So this is the last idea, which is a little bit harder for you. I know that, but I have to talk about it. So you understand rate for real. So A prime at 2 is like this. Let us one more time analyze A prime. What is A prime? A prime is basically the limit as h goes to 0. That's really the definition. So I'm going back to its definition. That's really what it is. Okay, so the change of the output over the change in input, when the change of input is very, very small. It means if we increase the area by the radius by tiny bit, the area changes. How fast it's changing with respect to the radius. So this means that the derivative is almost equal to this ratio. When h is small. Okay. All right. It means that I'm going to multiply by h across. I'm going to multiply. This gives me that A prime at 2 times h is almost equal to that. Because that's the slope. The slope is A prime of 2. So this tells me the following. That the change in the area is almost equal to the derivative at 2 times the change in radius. All right? So this is change in radius. And this is the change in area. All right. So let us read this. It means that when you change the radius by a little bit, so that's really my picture here. That's the radius, and that's the area. This is 2. The radius is 2. You change the radius by a little bit. So this is change in radius. You change this by a little bit. The area is actually going to change. And the question is, by how much it's going to change? So that's the change in the area. And this tells me that the change in the area is almost equal to the derivative at 2 times the change in r. So which means that the larger the derivative, the more the area change with respect to the radius. The bigger this, the more there is a change. The smaller the derivative, smaller is the change. So in the sense, the derivative is telling me how fast this is changing with that. How fast it is, because it's a multiplier between them. So the larger this is, the more we have changed. The smaller this is, the less we have changed in the area. Now that's really the idea that relate the derivative to the behavior of the function. So for example, suppose I tell you delta r, so let's change the area, let's change the radius by, let's see, half a centimeter. Okay, delta r, we change it by half a centimeter. What is by how much the area change? So this tells me that the area will change by that much. A prime of 2, which was, we computed it to be 12.56 times a half. So the area will change by almost 6.28 centimeters squared. So if I change the area by a little bit, the radius by a little bit, by half centimeter, the area will change by 6.28. Now, if I change the I change that by 1/4 of a centimeter, then the area will change. By how much? The derivative times 1/4. And the smaller delta r is, the better we have the approximation. It means the area will change by, 12 times this, so which is going to give me like 3.14, and so on and so forth. So the larger this is, the more the area changes with respect to the radius. The smaller the derivative, the less is changed. So the area, that's what the derivative is actually telling us. Okay, is this hard? Any input? All right. So now we're gonna move to section, the last section that involves formula, and then we're gonna go back to basically again try to understand the derivative better and apply it. I mean, we're doing a lot of formulas so far, and we're gonna start learning how to apply the derivative. But today we're gonna do the last formulas of hopefully this semester, and it's the derivative of the inverse trigonometric function. So this will put me on section 3.10 in the book, derivative of inverse trigonometric function. So let us first remember what is the inverse trigonometric function. So what are we talking about here? So what does the inverse trigonometric functions are? All right, suppose I ask you the following question. We're gonna go back to the sine of cosine. So what we studied so far, the sine. So if I tell you sine theta, what sine theta is, basically you take the unit circle, that's the sine, and you find the y coordinate, and that's give me the sine. And we graph the sine. So we have the graph of sine, it went like this. Okay. Now we're gonna go backward. So what do I mean by backward? Suppose I give you the sine of an angle. So I told you, okay, the sine of theta is, let us say, equal 1/3. So I give you an angle. I don't tell you what the angle is, but I tell you the sine of this angle is 1/3. And the question is, what's the angle? Okay. But that's not an easy question. I mean, you don't know what it is, what the angle is, but there is a function which is called arc sine, or the sine inverse, which job is the following. You give it the value of the sine, the function will give you the angle, which is the inverse. So I give you the value of the sine, it's gonna give you the value of the angle. So we're gonna introduce a function called arc sine of 1/3, or the sine inverse of 1/3. This is going to give you, this gives the angle. And here I'm going to leave a big empty space because we're going to fill it, whose sine is 1/3. So it's going to give you the angle whose sine is 1/3. I know you guys have seen this. I'm just basically helping to remind you. But now here's the problem. Here's the problem. How many angles have for sine 1/3? Is it 1? Is it 2? How many of them? Back to you. So how many angles have sine 1/3? So suppose it's 1/3. Let me draw the unit circle again. How many angles have this sine? So this is 1/3. How many angles have the same sine? 1/3. Is it 1 angle, 2 angle, 5 angles? So how many angles have the value whose sine are 1/3? Infinitely many. Okay, that is this one, the one you draw. You go 2 pi, that's another one. You go another 2 pi is another one. So there are infinitely many because we keep adding 2 pi to it. Very good. But now I'm going to define a function such that if I give it the sine, it's going to spit out the angle. But how many is going to spit out? We're not going to want something that's going to spit out infinitely many. So the arc sine is going to give me 1 angle whose sine is 1/3. And so on this picture here, in this picture, that's the sine. So this is 1/3. There are infinitely many that have for sine 1/3. The arc sine will give me one of them. It gives me the one between minus pi over 2 and pi over 2. So it gives the angle between, and that's really the space between minus pi over 2 and pi over 2. Give me one of them. Doesn't give me all of them. Whose sine is 1/3. So arc sine 1/3 is going to be the value of the angle whose sine is 1/3. But which angle? It's the one between minus pi over 2 and pi over 2. It gives me one of them. Because if I know one of them, if I know this one, I know all of them. Because I can just look at the picture and add 2 pi's. So if I pick up my calculator now and I compute the sine inverse, so the sine inverse of 1/3, okay. All right, so sine inverse, sorry. You can see how much I use my calculator. So sine inverse of 1/3, I get an answer, 0.3. So the calculator gives me 0.339 radian. So it means that the sine of 0.339 radian is equal to 1/3. Okay, so that's really what the arc sine is. The important part to think about it, that's the angle whose sine is 1/3. The other important part about it, it's one of the angles. They don't give me all of them. Otherwise, this will not be a function. Okay, so now let us define the sine inverse in a formal way. So that's a function. It has an input and an output. So the sine inverse of x in general, or I usually prefer arc sine of x. I like the notation arc because it reminds me I'm talking about an angle. Okay, the arc sine right is the angle between minus pi over 2 and pi over 2, whose sine is x. Okay, in other words, y equal sine inverse of x, or y equal arc sine of x means that y is an angle whose sine is x. So it means the sine of x, means that the sine of y is equal to x. So this gives me the angle, so that's the angle. And not any angle, and that's the angle is between minus pi over 2 and pi over 2. So if you know the sine and you want the angle, you use the sine inverse function. That's give you the angle, but it gives you one of them. It gives you the one between minus pi over 2, pi over 2. Then if you want the other one, you just use trigonometry to figure out the other one. All right, now by the same token, we can talk about arc cosine and arc tangent. And they are important. Why they are important? Because a lot of time when you're solving a problem, you know the sine, you want to find the angle. So that's really the importance of that. So by the same token, we're going to talk about the arc tangent and the arc cosine. Those are the ones that we use basically the most. And then, as usual, we have arc secant, but it's the same definition. So what is arc cosine? Arc cosine or cosine inverse. Okay, both mean the same thing. Is the angle. And now here we have, I will talk about that. I'm going to leave an empty spot here, whose cosine is x. So cosine inverse is the angle. So the output here is an angle. The output here is an angle whose cosine is x. But the angle between what and what? Which angle? Okay, let me tell you which angle is here. I'm going to graph the cosine right there so we can discuss which angle. That's the cosine function. That's the cosine. It starts here, it goes down, it goes up. It starts here, it goes down, it goes up. This is a 0. This is pi. This is pi over 2. And this is 2 pi. That's how it works. And this is the minus pi over 2. Now, and that's the cosine function. That's the cosine. Now what's happening for the cosine? Suppose I want the cosine inverse of something. Let me call it 1/3. And I want the angle whose cosine is 1/3. Now, between here and here, minus pi over 2 and pi over 2, there are two angles whose cosine is minus 1/3. The cosine inverse has to give me one of them. So the cosine inverse is going to give me the angle between 0 and pi, whose cosine is 1/3, because it has to give me one angle. So I need, if I give you the cosine, I need one of them. The cosine inverse will give me the one between 0 and pi, because it cannot give me between minus pi over 2 and pi over 2, because there are two angles whose cosine is 1/3. So the calculator is not going to give me both. The calculator will give me one. We have a function. So it doesn't give me this one. It gives me the one between 0 and pi, because between 0 and pi, I only have one of them. So the cosine inverse is going to be the angle between 0 and pi, whose cosine is x. Okay. Now, finally, the tangent inverse, arctangent, or tangent inverse, is an angle. The angle between minus pi over 2 and pi over 2, whose tangent is x. Okay, so that's the arc cosine and arc sine. Now, for the tangent function, why it is between minus pi over 2 and pi over 2. If I think of the tangent graph, the tangent goes like that. That's the tangent graph. This is minus pi over 2 and pi over 2. So if I give you the tangent, there is only one angle between minus pi over 2 and pi over 2 whose tangent is what I give you. So suppose I tell you tangent inverse of 3, there is only one. There are not two of them. The calculator will give me that one between minus pi over 2 and pi over 2. So the tangent inverse gives me exactly that one. The sine, the cosine, I had issue. The cosine, that's the graph of the cosine. So if this is minus pi over 2 minus pi over 2, one angle, if I give you the cosine, there are two angles between minus pi over 2. That's why we don't take this part. We look for the one between 0 and pi because there is only one angle that will give you that. Okay, so that's the idea of sine and cosine. So they are inverse and sine inverse. They are important because they give, I have the cosine, I'm after the angle, then the arc sine will give it to me and the arc cosine, but doesn't give me all of them. It gives me one of them because it is a function. All right? So these are the arc sine and arc cosine, very important function that we will use a lot. Now, what is the derivative? And here I will just give you the formulas instead of really showing you, and we work with them. So these are the formulas for those derivatives. And believe me, you will use them, so we have to learn them. So the derivative of the inverse trig. Okay. All right, so we start. The derivative of arctangent, which is one of the most used one. Derivative of arctangent or derivative of tangent inverse is 1 over, I'm gonna hate me for that, 1 plus x squared. Okay, so you just have to memorize those. And the derivative of arc cosine of x, it means, or the derivative of cosine inverse is minus 1 over the square root of 1 minus x squared. So as I said, it's just to be memorized. There is not much I can do about those. And finally, the derivative of the sine inverse. And the book have the other ones, secant inverse and stuff, but I will not really make you memorize all those, is 1 over that, 1 minus the square root. Okay, so these are the derivative of the trigonometric function. They are just a bunch of formulas that we have to learn. Okay, now let us practice those formulas and practice a little bit the definition of tangent inverse and cosine inverse. Okay, so that's our definition and these are the derivative. So now we're gonna do, a problem. So first I'm gonna ask you some question concerning the definition of arctangent, and then question working with the derivative. Okay, evaluate the following. Evaluate, and please don't have your calculator with you. I want answers without a calculator. Evaluate. Sine inverse of 0 or arc sine 0. And because you justify. I want you to evaluate cosine inverse of a half. Okay, all right. Let's start with the first one. What's the sine inverse of 0? Put them on the sheet, on chat, sorry. What's sine inverse of 0? What's the angle whose sine is 0? So sine inverse of 0 is, I'm asking for the angle whose sine is 0. Which angle? Be very careful. Sine inverse of 0 is the angle whose sine is 0. Which angle have sine 0? It's 0. Why? Because sine of 0 equal to 0. Okay, that's the sine inverse. It's the angle whose sine is 0. Part 2. What's the cosine inverse of a half? Means what I'm asking you about. I'm asking you cosine of what equal a half. Okay, that's the cosine inverse. It means what's the angle whose cosine is a half. Try to go in your memory over the values of the cosine. Okay, all of you, please. I want an answer. What is the angle whose cosine is a half? Do you guys remember? You should know those basically by heart. Anybody? Come on, guys, you should know. What's the cosine inverse of a half? What's the angle whose cosine is a half? Pi over 3. I am after the angle. Okay, let's keep going. What is of square root of 2 over 2? It means what is the angle? What is the angle whose cosine is the square root of 2 over 2? Back to you. That's the easy one. Pi over 4. Okay. Now, what is tangent inverse of 1? It means tangent of what equal to 1? Which angle has for tangent the value 1? So this is, we have to practice that. Okay, back to you. Pi over 4. Absolutely, because what's the tangent of pi over 4? Let us remember, what's the tangent of pi over 4? The tangent of pi over 4 is the sine of pi over 4 over the cosine of pi over 4. But the sine of pi over 4 is square root of 2 over 2, which is equal to 1. Okay, absolutely crucial numbers. All right, practice one more. What is the tangent inverse of 0? Means I'm asking tangent of what equal to 0? Okay, that's what those arctangent is. They are crucial. Which angle has for tangent 0? Remember, tangent is sine over cosine. So sine of what over cosine of what give you 0? That's what I'm asking. That's what the tangent is. Which angle, sine over cosine, give you 0? Absolutely. Tangent inverse of 0 equal to 0, because tangent of 0 is equal to 0 in this particular scenario. All right, so the arctangent is the angle. It's the angle. So I'm asking you about the arctangent. I'm asking you about the angle, whose tangent is what's given. Tangent inverse of 1 is the angle, whose tangent is 1. Okay. Now we try to compute a bunch of derivatives. So find the derivative of the following. Okay. So the first one is y equal tangent inverse of 1 plus x squared. Okay, tangent inverse of 1 plus x squared. And here I remind you what's the derivative of tangent inverse. So right here, the derivative of tangent inverse, because the derivative of that is 1 over 1 plus x squared. And now I want the derivative of the inverse tangent of that. So what are we gonna, what this problem is? It means what is this? A chain rule, a product rule, a quotient rule? What is this? Tangent inverse of something. So that's immediately the chain rule. Okay, so what's my inside and what's my outside? Crucial. My inside is my inside. That's my u, or g of x. My outside is the tangent inverse. That's my outside. So what is my derivative? So it's like always the same thing. It's the derivative of the outside, but you evaluate at the inside. So what's the derivative of the tangent inverse? So it's 1 over 1 plus your inside to the power 2, because that's my inside, times, So the chain rule is a product of derivative times the derivative of my inside function. So y prime equal, so now we're doing what we've been doing for a long time. The derivative of 1 plus x squared is 2x. 1 plus 1 plus x squared to the power 2. Okay, so that's really my derivative here. Okay, let's try another problem. So let f of x equal, let's practice the sine inverse a little bit. Sine inverse of 1 plus e to the x. Okay, and the question is find f prime of x. Okay, all right. So since there is a sine inverse, I'm going to here remind you the derivative of sine inverse. So the derivative of sine inverse is 1 over the square root of that. That's the sine inverse. Now again, the sine inverse of 1 plus e to the x. This is my inside. That's my u. So what's going to be my f prime? Okay. It's the derivative of the sine inverse, which is 1 over the square root of 1 minus evaluated at the inside. It means instead of x here, I have to put my inside. Times the derivative of my inside. Now I put my inside here, and I put my inside in here. So that's the derivative of the outside evaluated at the inside times the derivative of the inside. The rest is actually the same idea. So it's 1 minus 1 plus ex squared times the derivative of the inside is e to the x. Okay, so applying the formulas is again the same ideas, chain rule and chain rule and chain rule. Okay, all right, so that's it for today. Please do your homework for tomorrow. And tomorrow we're gonna start, as I said, applying the ideas. So we're done with formulas with that. And tomorrow we're gonna start using this derivative. Okay, all right, you guys have any questions? All right, bye-bye for now. Thanks.